want from you guys, I want you guys to go ahead and work on atomic structure bell work number 5. Atomic structure bell work number 5. This has some review, some of the orbital stuff like that, blah, blah, blah. And there's some orbital diagrams on the back, the little bubble charts. So go ahead and knock this out for several minutes, and then we're going to get cooking on some new stuff, and I'll give you guys the plan for this week and next. So work on atomic structure bell work number 5, please. So let's go ahead and talk about this bell work, orbits versus orbitals.
An orbit is when something like revolves around
Mhm.
something, and an orbital is just a space where 0 to 2 electrons might be.
Okay, pretty good. So an orbit, which was kind of the idea was kind of come up with by Bohr. So that's when electrons are in predictable paths around the nucleus. Basically, like, okay, the electron's going to be here at this time and here at this time. Like, we should know generally where an electron is at any given point. We know that's not actually the case. It's a nice idea, but that's not actually the case. Whereas an orbital, that's like a region of space with a high probability of finding an electron. So maybe the one thing I would change a teeny bit there, Aurora, is that it's very likely that the electron's in there, like a 90% chance. So an orbital, remember my room 245 that we're currently in, is my orbital. Mr. P is probably in room 245 at any given point in time during the day. You don't know that for sure. You're like, he's probably there. I don't know if he's like in the corner of the room, by his computer, up at the front, but I know he's somewhere in this space, okay? What are the different shapes? Let's see here. For S.
Sphere.
Sphere, right? S, you can think of it as like a sphere, so just like a ball, basically. It's the shape of an S orbital. What about the P, Uzama?
Pair.
Pair, yep. So it's going in the y-axis, the z-axis, and the x-axis. If you were drawing this on your paper, you might have drawn something like this, which is perfectly fine. And what about D? D for Daisy. So these are what these all look like again. This last one's kind of weird, but if I was drawing one of the D orbitals, I'd draw something like this. It's like a p orbital crossed by a p orbital, just something like that. Okay? So there we go. You just want to make sure you can recognize those shapes. Off-bound principle. Grace, talk to me. What the heck is this off-bound principle?
Just like where you fold electrons starting from the bottom and
Yeah. So you want to start electrons from the bottom, which is the lowest energy level. That's the key idea. That's why we start from the bottom and fill your way up. Okay? So electrons are lazy. They'll fill the lowest energy level possible before they move up. And again, lowest energy levels are closest to the nucleus. Okay? And lastly, Hund's rule. Jack, talk to me about this. Hund's rule.
You only put one electron in each orbital before doubling up.
Absolutely. You only put one electron in each orbital before you double up. Electrons do not share well, so you only put one electron in an orbital at a time. So if you had some p orbitals here, okay, you'd be like 1, 2, 3, and then when there's no other choice, this fourth electron would be like boom. Okay? The reason why electrons don't like to double up in orbitals until they have to is because they both have a negative charge, and that negative charge repels each other. That's why electrons aren't big fans of each other. All right, so now talk about the orbitals. It's here. We'll do germanium. That was one of the ones on the back. If germanium is neutral there, let's see here. What's the atomic number, first of all? Somebody tell me, what's the atomic number? What's that? 32. If it's neutral, how many electrons does that mean it has? What's that? Yep. If it's neutral, its protons and electrons are going to be the same. This will not always be the case. You've been warned. It's not always the case, but this is the key thing we have to find out. We have to find out the number of electrons. For these problems, the atomic number of electrons has been the same for most of them. But that's what we need to know before we can fill out the bubble chart and do the electron configuration. Okay. Well, remember that the nucleus is somewhere down here. Okay. I'm going to fill from the bottom to the top, that is lowest energy level to highest energy level. And I'm only going to put one electron in an orbital at a time until we have no choice but to fill them up. Okay? So off-bound principle means I start down here. Hund's rule, this electron will pair up because there's nowhere else to go. Boom, boom. Electrons 5, 6, and 7 will stay separate. Okay? Electron 8 has no choice but to pair up. Okay? 9 and 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. They're all separate because of Hund's rule. 25, 26, 27, 28, 29, 30. Just like that. So we have our 32 electrons. Notice how the last two are in 4p. They're all nice and separate. Hund's rule. So in terms of the electron configuration, we're just going to read the chart. So I see 1s first. It has 2 electrons in it. I don't know why that always comes up. I see 2s. It has 2 electrons in it. 2p has 6 electrons in it. 3s has 2 electrons in it. 3p has 6 electrons in it. 4s has 2 electrons in it. 3d has 10 electrons in it. And the 4p only has 2 electrons in it. And so that would be the proper electron configuration. I will not ask you to give me the electron configuration for anything without also providing you a bubble chart to do so. Okay? So I will provide you a bubble chart to do any electron configurations for now. There will come a time where I'll ask you to do electron configuration without a bubble chart, but that won't happen until after winter break. Okay? So that's our bell work. Now let me talk to you guys a little bit about the structure of this week and next week coming up. So tomorrow, we're going to cover the last little pieces of information that could be on the Unit 4 test. Okay? Your Unit 4 test is on Friday of this week. And there won't be anything new after tomorrow. Okay, so once you are done with class tomorrow, you're like, all right, all this stuff is upstairs in my brain that I need for Unit 4. I just have to make sure I'm ready to play come Friday. This Thursday, before that Unit 4 test, virtual folks, you guys don't need to see me that day. That's a lab day. Live folks, do you guys remember the flame test lab where you took your notes for like, okay, this flame looks like this flame looks like this? That day I'm going to give you 2 test tubes with unknown chemicals in it, and you got to tell me what's in them. Okay? So remember, make sure you have beautiful flame test notes. You'll be able to use your own notes, but that's all you get to use. Okay? So make sure you're ready for that. Next week, we're going to have our semester exam. Okay, so next Thursday is our semester exam. You're like, Mr. Professor, I thought there weren't exams this year. So this exam is going to cover units 1 through 4. Okay, so I want to see where you guys are at. But it's also not nearly as difficult as my normal semester exam. Okay, my normal semester exam is very difficult. Okay, but this one's just sort of trying to feel out where you guys are, kind of wrap things up, put a bow on the first semester. Okay, you will need to study, and it will be difficult. I will give you a review packet, all that good stuff. But just know that we do have a semester exam scheduled for next Thursday. Okay, so that's what we got cooking. That's what we have coming up. Yeah. And you virtual folks, you will do the second half of the flame test next week. Now, we got to take a few more notes today. Pretty brief stuff. Let's see here. We got to talk a little bit about excited state and ground state electrons. Now, right now, you don't need to take your notes, but you will want to turn to a specific page in your packet. So you need to find the front page of History of the Atom Notes, part number 5. So you're actually going to go a little backwards in your packet. History of the Atom Notes, part number 5. You want to go to the back of that notes page, in the bottom half where it says Aufbau's principle in a nice little dotted box. So again, we're on the back of History of the Atom Notes, number 5. And we're looking at the bottom half where it says Aufbau principle. Okay? All right. So right now, you don't have to take any notes. I'll tell you here momentarily. But let's remember how light works, okay? So remember, first thing is that electrons are in their ground state, where that means they're closest to the nucleus and they're low in energy, right? So like this guy right here. The next thing that has to happen. So a lot of people wanted to say on the quiz last week, they're like, okay, so then the electrons become excited. No. Electrons can't become excited unless something causes them to be excited, okay? So the second step means you have to add energy. That comes first. You have to add energy in some way. There are a lot of ways to add energy to electrons. You can put them in a flame, like the flame test lab. Here, you know what's another way that you add energy literally like every day of your life probably? When you flip a switch. Every time you flip a switch, a light switch is basically like, it's sort of like, picture like a dam, okay, where it's holding back a bunch of water. Once you open up that dam, then the water can go through. Light switches are basically like energy dams. The moment you flip the switch up, you're allowing energy to fly through to whatever device is connected to. Okay? So whenever I turn on my light switch, I'm sending energy into my light bulbs. Okay? So there's a brief moment in time, it's like a billionth of a second, where I turn the switch on, and there's energy in my light bulbs, but there is no light yet. Okay? Once you do add energy, though, the electrons will become excited. They will go farther from the nucleus. They may take a little baby jump, like, whee! They may take a huge jump, okay? But they'll jump up to some higher energy level, okay? Could be 1 level up, 10 levels up, whatever. What goes up must come back down, right? So the electrons will fall back, and the only way they can fall back, though, is if they throw that energy off, that extra energy off. And when they throw the energy off, it's in the form of photons, okay? Different forms of energy will give you different colors, okay? So you may remember, red is like low amount of energy, violet is like the highest amount of energy, green is like a medium one. So this electron light right here, let's say it fell from here to here. That's a small gap, okay? Maybe it gave off a little energy, that might be some red light. But if it falls from here all the way down to there, that's a pretty big gap. That would require a lot of energy to be released. Maybe that photon is purple or violet, okay? So again, this is just a reminder right here about how light works. You will be asked quite extensively about this on Friday. Now let's talk about ground state and excited state orbitals. Now think about this. So Aufbau's principle, if we're actually looking at the notes at this point, we're actually looking at the notes here. We have that little box that says Aufbau's principle. Electrons start at the lowest energy level and fill up from there. Now, what situation is a violation of this principle? When do we ever violate Aufbau's principle? Is there ever a time where electrons are not at the lowest energy level possible? Yeah? When they become excited, okay? So when an electron's excited, it's temporarily not at the lowest energy level possible, okay? So, remember, again, you don't have to write this part down. Remember, ground state, low energy, electrons close to the nucleus. You add energy, and they'll become excited, so they're going to go farther from the nucleus. So let's do an example here. On your paper, you guys have neutral sodium, okay? So sodium, it has... if it's neutral, it's going to have 11 electrons, okay? 11 electrons. So, how many electrons we need to put in here? Well, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that last electron will go into 3s, okay? Now, to draw an excited state sodium, here's what you need to do. I'm going to draw those same 11 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Don't do this last part in pen. I will draw this here for a second. So I need to take at least one electron and move it up at least one level. I personally like to just take the highest electron and just move up to the next one right there. That's excited. I could have done anything now. I could take this one electron, move it there, here, here, any of these guys, any of these, literally any of this stuff above, okay? As long as I move at least one electron up at least one level, it's an excited state, okay? Unless I give you more information and tell you exactly which level it's going to. If I say excited, you just grab one, throw it up there somewhere. And you could, if you're really feeling saucy, you could just start grabbing a whole bunch of them and be like, yeah, we're actually going to take a little field trip. We're going to go, like, up here or something. I don't know. Like, okay, so you can move them wherever, but, oh, now they're gone. Where'd they go? Come here. Sorry, buddy. There we go. As long as you move at least one up. Now, again, so this excited electron right here. Oh, I erased them. Come here, little fellow. This excited electron right here, okay, it will fall back down eventually. And it will give off that energy, etc., etc. Okay? So that's one thing I want you guys to understand about bubble charts. I may ask you someday to draw an excited state electron compared to the ground state, or recognize such a thing. Okay, so here's what I want from you. You will do your Monday lecture quiz in the Monday folder right now. Okay, so go ahead and knock that out for me. After you do that, you will work on orbital charts practice number 2. After you do that, you will work on orbital charts practice number 2. Okay? Virtual people, once you knock out that Monday quiz, you guys can go ahead and get out of here. Live and virtual folks, once you knock out that quiz, work on orbital charts practice number 2. The answer key to today's spell work and this worksheet right here are both in the Monday folder. Okay? Live folks, we are going to be doing some sweet demos, which you virtual folks will be doing next week. Live folks, we're going to be doing some cool demos involving triboluminescence today. So it should be pretty fun. So virtual folks, once you guys knock out that Monday quiz, you guys are free to go. Just make sure you work on orbital charts practice number 2.